you feel like you understand the single bond shenanigans, it's time to level up. Time to go to double and triple bond. By the end of this lesson, you should be able to use Lewis dot diagrams to show double and triple bonds between nonmetal atoms. In order to draw double and triple bonds, we first have to know what they are, and then we're going to learn some exceptions and apply it all. Again, for those of you watching my videos, if you're an educator and you like these timelines of the lessons for knowing what the Bloom's taxonomies are for your lesson structure, please check that out in the description below, which is where I'll be putting these timelines from here on forwards. If you haven't watched my video yet on single bonding, then some of this might not make sense. You might want to click on that video in the description below in order to get yourself educated on single bonds first before we move on to double and triples. Anyhow, what we see is that sometimes when we're pairing up atoms together and we've got all of the lonely electrons, all the lonely electrons, where do they all come from? Sometimes one line isn't sufficient to fix the problem of each atom wanting an octet. So sometimes we need to pair up multiple lonely electrons when we only have a certain number of atoms present to do so. So they're going to share multiple electrons with each other in order to fix this problem and have their full octet for each atom to be happy. And this is where the double and triple bonds come into play. If we have to draw more than one line from one atom to another, then we end up with a double bond, or if we draw 3 lines to connect 2 atoms together, we end up with a triple bond. Please keep in mind that bonds are designated by a straight line, and a straight line is composed of 2 electrons per line. So therefore, if we have 2 dots, 2 electrons, that's equal to 1 line or 1 bond. Hold on, let me shrink for a second. I need to get out of the way of this. All right, there we go. Okay, so if we have a double bond, however, we have 2 electron pairs that are shared between atoms. That would be equivalent to 2 lines and 2 bonds. So altogether here you would have 4 electrons. So 2 electron pairs is equivalent to 4 electrons within 2 lines equivalent to 2 bonds. So now what if we have a triple bond? A triple bond would be 3 electron pairs, so 6 electrons total, 3 lines, 3 bonds shared between 2 atoms. So following up with the same picture that I had on the previous slide, if we have nitrogen, for example, which is a diatomic gas, N2 has 3 unpaired electrons. So poor lonely electrons shivering in the cold and they want to find a mate. And an N2 is signifying that we have 2 N atoms, and those N atoms are all they got. They only got each other. And each N has 3 lonely electrons on it. How convenient that there's 3 lonely electrons on each N atom. They can just share those and create a triple bond. So if you're not sure where these lonely electrons are coming from, here's a few arrows. So those are the 3 lonely electrons I'm talking about, and they're going to pair with the same 3 lonely electrons on the other nitrogen atom in order to create this triple bond. Let's see if you understand the concept by trying it with oxygen, O2. All right, so stemming back to our Lewis dot diagrams rules, or the steps that we use to draw Lewis dot diagrams, we're going to do the same thing for double and triple bonds as we did for single bonds. So first things first, we have an O2 molecule right there, and that O2 is implying that there are 2 oxygen atoms. So we need to draw O and O. O, 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 it's magic chemistry. Anyways, we've got O2, 2 O's. Now the next thing we need to do is figure out O's valence, oxygen's valence number. You need to look at your periodic table in order to determine this. If you count over, we use our little shortcut, then we're just going to count by columns. 1, 2 for those columns. We skip all the transition metals. We go 3, 4, 5, 6, and that's where oxygen's located. It's in the 6th column, right before the halogen column, which is the 7th column before the noble gases. We know that oxygen then has 6 valence electrons. So we're going to play ring around the atom. 1, 2, 3, 4, 5, 6. We need to do this for each atom of O. 1, 2, 3, 4, 5, 6. What we see now is that we have two paired electrons on each oxygen atom. We call these lone pairs. We're going to leave those alone. They don't participate in bonding between atoms because they're happy. They've already got a mate on their own atom. So these guys right here are the ones that we're going to leave alone. Those are our lone pairs. And they're already happy because they're already in a pair. However, we do have some lonely electrons that I see. Each oxygen atom also sports two lonely electrons. Here, poor lonely electrons. We need to hook these electrons up in order to make oxygen happy in that it has an octet for each atom's perspective. So we're going to move on to step 3 of our Lewis dot diagrams and connect our lonely electrons. We've got one lonely one here to there, one lonely one here to there. Of course, we're not going to leave it like that. That looks atrocious. We would never turn in a paper like that to your chemistry teacher, right? Don't do that to them. So what we need to do now is clean up this molecule, make it look pretty, with the solid lines between the atoms and keeping all lone pairs still visible. Let's redraw this. So redrawn, we have an oxygen with two lines between them. That's this line and this line. And we also have two lone pairs on each oxygen atom. Now we have a molecule of oxygen, and that would be our final answer. Notice that a molecule of oxygen has a double bond. There are two lines, that is a double bond, or 4 electrons total, because each line represents 2 electrons connected. Now, before we continue with more practice of these double and triple bonds with our Lewis dot diagrams, we need to understand a few exceptions that you may encounter when it comes to drawing these double and triple bonds. The first exception is hydrogen's exception. Hydrogen only needs 2 electrons to be happy. So anytime you have a hydrogen present, it does not need an octet. Do not try to give hydrogen an octet. It'll have a fit. It only needs 2. So remember that if hydrogen has 2, you're good. In other words, hydrogen breaks the octet rule. It's a rebel. There's also an exception for boron. Boron, B, tends to form compounds so that it has 6 electrons. So it doesn't necessarily want to have 8. It's content with 6. It also breaks the octet rule in that it's happy with 6. Let me show you what I mean by drawing BF3. In BF3, we have 1 boron atom and 3 fluorine atoms. So we need to draw each atom out respectively and their individual Lewis dot diagrams according to our previously learned steps. We have 1B, we have F, F, F. Well, first let's see where boron and fluorine are located. Boron is going to be a valence of 3 because if we use our little shortcut, we've got 1, 2, skip all the transition metals, and then that column that boron is in is 3. How about fluorine? If we use the same shortcut, fluorine is in the 7th column, so it has a valence of 7. So we need 3 for boron, 7 for fluorine. Let's play ring around the atom. 1, 2, 3 for boron, and 7 for each fluorine. 1, 2, 3, 4, 5, 6, 7. I'm just going to make the other 2 look the same. Now remember, we're going to leave lone pairs alone. They're already happy, they have a partner. So ignore all of those lone pairs for now. We don't need to think about them. We need to think about all of the lonely electrons that need to have a date. They need to be made happy. Conveniently, we have 3 lonely electrons on B, and we have 3 total lonely electrons, 1 contributing from each fluorine atom. Let's play connect the lonely electrons. We'll just connect this one here. It doesn't matter which one you connect to where, you're just connecting to make sure that all of the lonely electrons have a mate. So you could connect this one here, and then we could connect that one there. Again, the order in which you connect them is not important. You can connect them any which way. Our 4th step is to figure out which one of these atoms is least electronegative so we can put it in the middle. In this case, boron is less electronegative than fluorine, and fluorine is the most electronegative atom on the entire periodic table. So fluorine is going to go around the outside. So we're going to put B in the middle here, and we're arbitrarily going to put F's around it. Where you put it around it doesn't matter as long as you're kind of surrounding the B in some way, shape, or form. We also need to draw a single line between each, like that. And we need to carry over our lone pairs, our lone electron pairs on each fluorine atom. I know it's tedious, but don't skip this step. It's important. It's not complete without all those lone pairs. And this would be your final answer for BF3. Notice that boron, according to boron's perspective, it only has 6 electrons. Each bond is composed of 2 electrons. So from boron's perspective, it only has 6 electrons, and it is happy with that. It doesn't need 8. However, from fluorine's perspective, each fluorine has an octet because it wants an octet. So this fluorine has 2, 4, 6, 8. This one has 2, 4, 6, 8. This one has 2, 4, 6, 8 altogether. But from boron's perspective, it only has 2, 4, 6, and it's fine with that. And our final exception is called expanded valence. So these are the atoms that are actually happier with even more than an octet. So phosphorus and sulfur can literally split up 2 happily paired electrons to make more bonds to itself. So whereas all before we were leaving those lone pairs alone because they already had a buddy, phosphorus and sulfur are like, nah, we're going to break them up and hook up with a different atom because that's way more appealing. Keep an eye out for other atoms that can do this too. Phosphorus and sulfur aren't the only ones, but they are typically the ones you will see. So be on watch for any central atom that has 5 or 6 bonds, and that would be indicative of expanded valence. Let's give one of these a try just so you can see what I mean by splitting up the lone pair to make the bonds work. If you were to look at your periodic table and look at phosphorus, it would have 5 valence. It's right below nitrogen, and it has a valence of 5 according to our little shortcut of counting columns all the way over. In PF5, we have 1 P and 5 Fs. And we already learned before that F has a valence of 7. We have 1 P and 5 Fs. 1, 2, 3, 4, 5. Let's draw our 5 valence electrons around phosphorus. Play ring around the atom. 1, 2, 3, 4, 5. And now let's play ring around the atom for all of our fluorines, which each have 7 valence. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Whew. Okay, now we need to leave the lone pairs alone on all the fluorines, but for phosphorus, we're going to need to split up that lone pair in order to make a bond between all of these fluorines to the phosphorus. So this lone pair right here is about to get broken up. Reality TV time, guys. This is the breakup of the century. But first, let's connect all the other ones so you can see why we're splitting up this happy couple. We have a bond here, we have a bond here, and we have a bond here. We need to make one molecule while all of these are connected to each other. So we would not connect fluorine to fluorine here because that would result in PF3, F2. Those are 2 separate molecules. That's not going to work. We're trying to draw PF5, so they all need to be connected together to the same central atom. So now it's time to split up our happy lone pair so that they can bond separately the remaining fluorine atoms. And they're split up, broken up, sad day. Now that they're split apart, they can now bond with fluorine atoms that are left. So our final product would be cleaned up and look like this. There she is, our expanded valence example of PF5. Phosphorus has a total of 10 electrons instead of 8, and it's happy with that. Let's summarize what we know so far before we really test ourselves and draw some more challenging molecules using double and triple bonds all together. The number of dots around each atom, each central atom, is the valence electrons, and you get that number from the periodic table using either a shell model, an orbital diagram, or an electron configuration, or just use the shortcut that I've been telling you, 1, 2, skip transitions, 3, 4, 5, 6, 7. That's a much quicker way of figuring out what the valence is. You're going to put together any lonely dots to each atom so that each atom has 8 total valence electrons from its perspective because it wants an octet, other than hydrogen and boron because they want less, and sulfur and phosphorus could want more. Remember those exceptions. Remember that typically all of the atoms want their lonely electrons to be paired up. They want to connect those lonely electrons. Sometimes you have to do this with double and triple bonds to fulfill it. Keep an eye out for all those exceptions: boron, hydrogen, phosphorus, and sulfur. And always, always clean up your molecule before you turn it in so your poor chemistry teacher's eyes don't do this as he or she is trying to grade your paper. You ready for the really challenging ones here? Let's give it a go. These are our organic molecules, organic meaning that there's carbon present. Anytime we see carbon in a molecule, it's considered organic. Since each of these challenge ones are going to have carbon in them, let's figure out what carbon's valence is first by looking at our periodic table. Carbon is number 6 on the periodic table, and if we use our shortcut, we count over 1, 2, 3, 4. It's in the 4th column, so it will have 4 valence electrons. In ethylene, we see that there are 2 carbons and 4 hydrogens. Let's individually draw each atom first. 2 carbons, and we have 1, 2, 3, 4 hydrogens. Now we need to draw the valence electrons around each atom respectively. Carbon has 1, 2, 3, 4, as we just determined. 1, 2, 3, 4. And each hydrogen, hopefully you have memorized by now, has a valence of 1. We now need to connect all of the atoms together. We need to note that there are 4 spots for each carbon to bond, and we need all of these to be connected together. What you would not want to do is this. You're not going to connect all of the carbon ones together and then the hydrogens separately. Those are now 3 separate molecules. That would be equivalent to H2, C2, H2, and they would all be their own molecules. This does not work. This is not the same thing as that. C2H4 is what we're going for. They all need to be connected to each other. So what we do want to do is figure out first, okay, how do we get the H's connected to the C's? We're going to connect some of these lonely electrons here, connect these lonely electrons here, and then we notice that there are still 2 lonely electrons on each carbon. Thank our lucky stars, we know about double and triple bonds, so carbons can connect to each other now, like that. Our final cleaned up drawing would be 2 carbons with 2 lines between them, so a double bond, and then there would be a single bond to each hydrogen. Now that would be our molecule of ethylene. Fun factoid about ethylene, it is one of the starting chemicals for many industrial syntheses, so creating other chemicals from it, and it's used to help ripen fruit. So it has kind of this musky odor to it, and it's a gas, and when you put fruit in contact with it, it helps ripen it faster. Let's try acetylene. In acetylene, we have 2 C's and 2 H's. So we need to draw 2 carbons, and we need to draw 2 hydrogens. As we saw before, each carbon has a valence of 4, so let's play ring around the carbon. Each hydrogen has 1 electron to share. Let's connect all of those lonely dots. We need a hydrogen connected to a carbon and a hydrogen connected to a carbon. Now you might ask, why didn't I put the hydrogen over here and connect it to this one instead? If we did that, then we would have this connection and this connection, but no way to connect these 2. Now you might say, well, couldn't they just be a lone pair? We don't want to draw carbon with lone pairs on it. Remember, carbon isn't very electronegative. Oxygen, nitrogen, fluorine, those are electronegative atoms. They're okay having lone pairs. They like it, actually. Carbon, not so much. So we don't want to do that configuration. All right, back to what we were doing. Now we see that each carbon has 3 lonely electrons that we can conveniently pair together. If we have 3 lines going between the carbons, we then have a triple bond. 1, 2, 3. So our final product would look like this. Oh, so lovely. There's your acetylene. What is acetylene? Acetylene is a colorless gas that you can use as a fuel. Now this last one here is quite the challenge. This is for acetone. So if you have ever used nail polish remover, that is what you are trying to draw the molecule for. I want you to give this one a try, and I will show you how to do it in a subsequent video. Just as a little hint to help you along with this one, there are 3 carbons in acetone, there are 6 total hydrogens, and there is 1 oxygen. Remember, you need to draw each of those individually and then try and connect all the dots together. Carbon and hydrogen are not okay with lone pairs. Oxygen is. Try and see if you can figure out that challenge question. If this video was helpful to you, please make sure that you hit that thumbs up button. Show a duck some love, please, and subscribe to my channel if you haven't already. See you for the answer of how to draw the Lewis dot diagram structure for acetone. Keep it quacky.
No ducks, no glory.